Welcome everyone to this video tutorial. My name is Victor Cutillas and we consider that this information could be useful for you because we experienced some troubles with the shortages of helium of the last year. So we started to work with an alternative to helium-based instrument. So today I will talk about the evaluation of hydrogen as an alternative carrier gas for GC-MS analysis of pesticides. First of all, it's important to understand that helium is not an abundant element on our planet. The majority of helium originates from the radioactive decay of uranium and thorium. This gas is located under the Earth's crust alongside other natural gases. When the helium concentration surpasses 0.3%, it is commercially extracted from natural gas. In recent years, there have been significant shortages of helium that have impacted different scientific fields. Although the figure I'm referencing here is from 2012, the world's helium reserves haven't changed significantly. It's important to highlight that the largest usage of helium is in cryogenics, primarily because it's employed to cool magnetic medical devices. So in our lab, instead of helium, we are using this hydrogen generator. To use it, you simply refill the bottle with molecular water every 3 to 4 days. The device will auto-load the required amount of water for the electrolysis. It also comes equipped with safety features, including automatic shutdown if a leak is detected. Here we can observe the Venn diagram of the usual carrier gases used in GCMS. We work at the linear velocity of 70 centimeters per second, and hydrogen here has the highest diffusion coefficient and the lowest viscosity. So in summary, using hydrogen, the chromatographic performance is improved and the analysis time is reduced. So the question is, if hydrogen is so good, why aren't more labs using it? So let's see. This table here outlines the pros and cons of the three primary gases used in GCMS. As we already saw in the previous slide, hydrogen exhibits superior diffusivity properties and lower viscosity values. On the other hand, helium is pricier and less available. But we must consider the innerness of hydrogen. Hydrogen in the ion source can produce the hydrogenation or dechlorination of some compounds, and to mitigate this, the source is coated with a unique amorphous silicon layer that reduces these kind of reactions. Moreover, due to the hydrogen's small molecular size and low viscosity, it's important to use the lowest flow possible to prevent compromising vacuum integrity. So, before starting the analysis, we inject a nitrobenzene standard vial and we monitor the 123 mass to charge ratio, which corresponds to nitrobenzene, and also we monitor the 93 mass to charge ratio, which corresponds to aniline. If the intensity of the aniline mass is dominant, it indicates hydrogenation inside the ion source. However, when the nitrobenzene intensity is comparable or surpasses that of aniline, we have the optimal conditions. This routine is essential to ensure minimal hydrogenation, and this check is especially necessary after days of system inactivity, where we can observe hydrogenation during the initial injections. Here we have an example highlighting compounds that are impacted by hydrogenation. The peak shape is being affected, and in some cases a general reduction in sensitivity can be observed. We just saw that the innerness is an issue, but there's another concern: the explosion risk using hydrogen. However, the gas chromatograph incorporates safety measures. The GC is equipped with an hydrogen sensor that automatically identifies hazardous leaks. The explosion threshold is at 4% hydrogen concentration, but the system will shut down if 2% hydrogen in the oven is detected. If we consider the typical oven size, which is 20 liters, and the carrier gas flow is usually around 1.5 milliliters per minute, reaching that 4% threshold isn't that easy. Moreover, as the oven cools between injections, it releases internal air, reducing the risk. So, with safety not being a concern anymore, our focus is to optimize sensitivity to match that of helium. So, with our equipment in Almeria, we proceed to evaluate the injection volume, ion source temperature, and detector voltage. So we optimize our current multi-residue method, and these are the final parameters. We use a PTV injector in splitless mode with 1 microliter injection volume. The ion source is settled at 280 degrees. We use a 20-meter column and a detector voltage set at 1.6 kilovolts. We also tested different liners, and these evaluations indicated that different liner deactivations with wool produce comparable peak shapes and sensitivities. However, liners without wool provide poor chromatography for several compounds and are not recommended. Here we can observe the chromatogram of 150 pesticides. The last compounds elutes at the minute 11.7, but we have 3 extra minutes of precondition before the next injection. And these are the final results of sensitivity. We made the evaluation in 3 different matrices: tomato, pepper, and zucchini, and the majority of compounds were identified at 10 ppbs. However, almost 80% could be identified at 5 ppbs. So with this multi-residue method, we can approach the sensitivity benchmarks of current analytical standards. Finally, we conducted parallel analysis of 15 real samples using both our helium-based GCM-SMS and our hydrogen-based system. The results were similar, but the hydrogen system usually quantifies slightly lower compared to the helium one. So finally, as conclusions, hydrogen is no longer considered a safety risk in the lab due to the numerous safety measures modern systems incorporate. While the diffusivity and viscosity values of hydrogen surpass those of helium, its lack of innerness must be monitored. Sensitivity is sufficient to identify 80% of compounds at 5 ppb, and the optimized method displays strong reproducibility and minimal strong effects. In summary, using hydrogen as a carrier gas in GCM-SMS appears to be a viable alternative to helium for the analysis of pesticide residues. Just to say thank you for your attention, and in the next slide I will present some questions regarding the topics presented. Hope this tutorial was useful for you, and again thank you for your attention.